and it all burnt, so the alarms went off. So here we go, 6.2. What I'm going to do with 6.2 today is kind of work you guys through a new way of graphing and working with polynomials. What we're going to talk about today is something called end behavior. End behavior is basically what's happening at the ends of graphs for polynomials. Now, polynomials are a lot of the stuff that you've been working with, quadratics, things of that nature. Quadratics we know are either up like a cup or down like a frown. Yep. So if they're up like a cup, their two tails, the right and the left-hand side, are both pointing up, which means they're heading towards positive infinity. The two tails are pointing downward, which way are they heading? Negative. Negative infinity. So as the values of x are getting larger and larger and larger, the values of y are going towards positive infinity. So as x goes to infinity, y goes to infinity. Same thing with the other way around, it just goes to negative infinity instead. Okay. A polynomial is basically, and this is just a real short idea, don't write all this out. A polynomial of a higher degree is going to be nothing more than where this a sub n stands for first term. The end value, x to the nth, stands for the degree. We put things in a descending order. I think by now you guys are accustomed to seeing things in a descending order. For example, 3x to the fourth plus x cubed minus 2x squared plus 4x minus 7. Yeah. That would be a polynomial. Okay. It's a polynomial of what degree? 4. How do you know that that's the degree?
Because that's the highest exponent.
It's the highest exponent. So the degree of the polynomial is going to be, when we deal with a polynomial, it's going to have like regular old integer values, okay? I should say integer, positive values, okay? It's going to have all positives from 0 on up. So degree is the exponent of the first term. Now I say it's going to be the degree of the exponent of the first term when it's in that descending order. And you can't have any negative exponents, okay? Or it's not going to be rational numbers. It's not going to be anything like the square root of 2 or anything like that. All right? No fractions either. We haven't gotten to that.
Nice.
We will get to it. They're fun.
Darn.
Okay. So what I want to look at is not only have polynomials, we have degrees. We also have a couple other quick things to look at. The zeros of a polynomial. You've done this. What would be the zero of a polynomial?
Zero.
Explain that more.
I have no idea.
How'd you find the zero of a quadratic? You set it equal to 0, yeah. So all you do is you set your polynomial equal to 0 and solve for whatever.
Again, this is a reminder that the drill
It's
has
where
included, and you can go back to your regular
the
class.
graph crosses the x-axis.
4x.
Solve Fox.
Solve faux x. Faux show. Okay. So it's where it's crossing the x-axis. Now, if you remember from the quadratic unit, you could have real zeros or you could have imaginary zeros. Today I'm going to talk more about real zeros, where it actually is. It's going to be factorable things that we'll be able to do rather quickly. So the zeros of the polynomial, you can have up to, I'm not going to run out of spot, I'm going to bring this down later. You can have n number of zeros are possible, where n is the degree. So if you've got a second degree polynomial, quadratic, how many possible zeros could you have? 2. Sometimes they're repeated. If they sat on the x-axis, remember that how I said it was just 1 0? We call that a multiplicity if it's repeated. You could have 2 zeros. You could have no zeros. It could be an imaginary zero. But like I said today, we're going to look at more of the real stuff. So if the n is the degree, that tells you the total possible zeros that you could have. So if you have a third degree polynomial, how many possible zeros could you wind up with?
3.
If you have a fourth degree polynomial, what could you have? 4, and so on. This idea of what's called a turning point, move this up a little bit. A turning point turning point of a polynomial is where the graph changes directions. Excuse me. And you can always have up to n minus 1 turning points. For example, if you have a quadratic, how many times does it change direction? Once. Up like a cup. It just goes back and forth. If you have, it has one change. It looks like that. If you have a cubic function, how many times can it change direction? 2. It could change twice, and it would look something like that. Same idea. If it's a 4th degree, you could have up to 3 of them because it's always one less. 4th degree polynomials might look like this: 1, 2, 3. Yeah, and so on. You can have all these things possible to happen. Yes, ma'am.
You keep saying like it's possible, so does that mean like it can still like have a 4th degree as well?
Correct. It could be a 4th degree polynomial. You'll see this a lot. You could have a 4th degree polynomial that has just one change of direction. Because sometimes in a 4th degree polynomial, you could have the real and an imaginary. And we're only going to graph the real side. All right? So those are the 4 little things that we used, but in order to see what direction the ends go, there's a nice little pattern that happens. So let's see. I need, what do we have? 1, 2, 3, 4, 5, 6, 7, right? Did I count correctly? I have 7. I need the 7 of you to come up here with markers and take your calculators and grab a marker.
There's 8.
Well, I only need 7 of you, so. Grab your calculators. Well, then don't sit. You sit down. Have you got your calculator? Oh, sorry.
I don't what am I doing? I don't even know how to do this.
Everybody else need a calculator? Lucio, first one. Olson, second one. Phillips, third one. You, 4th. 5th, 6th, 7th.
Wait,
All I want you guys to do is graph it. I want you to take a spot and draw what the graph looks like. Put it in your calculator and draw what the graph looks like. Okay? Put it in your calculator and draw what the graph looks like. That's it. Put it in the calculator and draw what your graph looks like. Let's label these. It'd be easier to label. This is 1, 2, 3, 4, 5, 6, and 7. Yeah. Put it in y equals and just sketch what it shows on your calculator. Put it on there.
Oh no.
Excuse me.
Change mine.
I thought I picked out ones that would work out normal for a normal window.
Mine aren't normal. Maybe.
Oh, nuts.
What are you guys supposed to have?
10 by 10s.
Oh, okay, never mind.
10 by 10 is usually normal. You guys try a couple too. Look at it.
You want us to write down all?
No, look at a couple of them. Just put them in your calculator. Just look at what happens. Look what happens at the end.
Numbers, do I? Hey, mister, I don't think this is right.
Hey guys, good question. If you don't know how to use the exponent button, how do you raise an exponent? There's the caret button.
I can't see anything.
That's what it looks like.
Are we supposed to like actually graph it with the correct numbers, or can I just like write the numbers? Mister.
Caret button is this one there.
It's gotta be like a drawing.
Okay.
Mister.
What's up?
I don't think this is showing up all the way. Maybe I'm right, or maybe I'm wrong.
Just draw it.
Yeah?
Yeah. Just rough sketch it best you can.
I guess. That's not very good.
There we go.
All right.
That's it, right there.
So what I want you guys to start paying attention to how they're starting to graph these things is I want you to see what's happening in the relationship between the first term with the first term's exponent. For example, if I'm looking at the first term on number 1, what's the first term on number 1? The coefficient is 1, right? It's positive or negative? So in this case here, that first term, that a sub n,
Sorry.
is positive.
There you go. Make it a little more clear for all of you guys.
Exponent, is the exponent odd or even? It's odd. And it's odd, and the graph kind of did this, didn't it? Okay. If I look at the second one, the second one had a negative first term. The first term is negative. The exponent is again odd. And what direction did that go? What did the tails do on that one? Did the opposite, didn't it? It did something like that, with other junk in the middle, but the tails did that. The third one was a quadratic. First term's positive and it's an x squared, so which was what? Up like a cup?
There you go. Mine was really wrong.
The fourth one was what? You've done the quadratic. What's the fourth one? Down like a frown. The fourth one was down like a frown because first term's negative, exponent was even. First term was positive, exponent was even. What about the fifth one? What's the first term? Positive. Odd exponents, which way is it going? Doing something like that? The tails are pointing in opposite directions? Increasing from left to right? Sixth one? What's that one going to look like? It's the opposite way. And then the fourth one, which way are the tails pointing? They're both pointed up, aren't they? Because it's positive and even. So what's happening here is you get this sense of no matter what, you can whittle this down to 4 possibilities. If you have even exponents, there's only 2 things that can happen. And if there are odd exponents, there's only 2 other things that can happen for the tails. And what I mean by the tails, again, are what's happening at the ends. So you have, we call them the dance moves. If you are even, it's good. If you are even and positive, you are pointing what direction? If you are even and you are negative, you are pointing down. If you are odd and positive, which way are you going?
One up, one down.
One up, one down, going from
Left to right.
and then if you're the other way,
Right to left.
that's all it is.
So
Yes,
put
ma'am.
that all together.
Wait, what is
For the exponent. The exponent being odd or even has to end.
what's odd even? What's odd even?
If it's odd, what I want you to think about this is, what is negative 2 squared?
It's down.
4, so it'd be pointing up.
First one is down.
If it's negative 2 cubed, it's negative 8. If it's positive 2 cubed, it's positive 8. See where I'm going with that? So you get these little rules, and it really depends if your first term is positive, and n for the degree is even, which way are the tails pointing? The tails are always doing that. There's a whole bunch of other junk in the middle, depending upon what kind of degree it is. If the first term is negative, and n, our degree, is even, which way is it pointing? Down. So what this allows you to be able to do is no matter what weird polynomial you get, you always know a part of the graph. You know what's happening at the ends. It always works. It'll always work. Same thing if we go with the odds. The odd exponent. So if the first term is positive, And n, the degree again, is odd. What are your tails doing?
Go.
They're
Going from left to right? They're doing that. In your book, in some textbooks, you might see them do this in between. Because you don't know what's in there. Or they might put like a cloud or a circle. But the essence that the tails, it's true, I've seen it. I've seen a cloud.
Like a jet cloud.
Can you scroll up real quick?
Yeah. And then the other one, if the first is negative, with the degree again being even. Oh, not even, excuse me. Odd. It's just going in reverse.
Yeah.
And to be honest with you guys, if you can remember what the x squared does, if it's positive or negative in the first term, and if you can remember what x cubed does, whether it's positive or negative, every other polynomial, if it's even exponent or an odd exponent, follows the same thing. It's ridiculously simple. Okay? But what we're going to do is take this information. Oops, where's all my erasers? I'm sorry. You'll get over it. What we're going to be able to do is take a polynomial like this. So we just did all that. And plot it without doing anything else besides that. By just being able to plot, find zeros, and go. And that's what that means. We're going to plot the tails, the ends, find our zeros, plot and go. These are quick, rough sketches. These are really, when you guys get to be honest with you, when you guys get to pre-calc, this skill is golden to be able to do. All right. This one here, if I want to look at the ends, what are the ends doing? They're both up, right?
Yeah.
So I know for a fact that both my ends are up. What are the zeros of that function? How do you find the zeros of a quadratic? Set it equals 0 and solve it, okay? So if I do that, I get x squared minus 6x plus 9 set equal to 0. So what times what's positive 9? You add together, you get negative 6.
3 and 2.
Negative 3, negative 3. So does this 0 repeat itself?
Yeah.
When it repeats itself, we say it has what's called a multiplicity of 2. It means it's just repeated. Okay. Now, if it's repeated, does it touch the axis in more than one spot? No, it just touches it where? Positive 3. So my 0 is at 3, so that means this graph would just be, there's my 0, and I know the tails are pointing up. Boom, done. And you can see why I wanted to just start with a quadratic, because you guys all know how to graph quadratics. But when you get to an upper level degree, you're doing the same thing. You just have to factor it a little bit further. Okay? So we're running short because of the drill here. Let me see if I can skip ahead here. When you have upper degree polynomials, in this case here I have 3x to the 4th plus 15x squared minus 72. First thing we're going to be able to do is what's happening at the ends.
Oh,
Are they both up?
No.
Why are they both up? Even and positive. Good. So we know the tails are pointing up. Zeros. I go ahead and factor again. 3x to the 4th plus 15x squared minus 72. Set it equal to 0. What's your first rule of factor?
oh, you gotta go.
Get out the 3. Good. If I take the 3 out, I get x to the 4th plus 5x minus 24 is 0. Does that 3 have... Oh, excuse me. Thank you. Does that 3 have any bearing upon the problem from here on out?
No.
Why is that?
It's gone.
Because I can divide out both sides by 3. Since it's set equal to 0, 0 divided by 3 is 0, no big deal. Now, do you guys remember the rule if you've got a 4th degree, 2nd degree, and you're constant? How do you factor that?
no idea.
the exact same way as you would factor squared x in constant. Because isn't x squared half of x to the fourth?
Yeah.
Same way. So let me ask you, what times what's negative 24 you add together to get positive 5?
Oh, 83.
Negative 83, right?
How do you do it?
So you could do x squared minus 8. Oh, x squared plus 8, and then x squared minus 3. Because if you FOIL that out, when you get x squared, or excuse me, x to the fourth, 8x squared minus 3x squared minus 24.
Yeah.
Okay. Do I have two terms that equal to 0? Yeah. Which one of those is going to give me imaginary? Which one of those is giving me a real?
The 8.
3 will be real, so what will be my two zeros then, Cody?
3 and 0.
Careful. X squared minus 3 equals 0. Wouldn't that be x squared equals 3? X equals plus or minus root 3?
Oh, got me.
Yeah. Okay. Now, we all agree that this is an imaginary solution, correct?
Yes.
Can we plot the imaginary solution?
Yes.
No. So here's what we do. Fourth degree polynomial. We have imaginary solution. We don't plot it, but I have root 3 and negative root 3. Can I say that they just go right there?
Yep.
We know the tails go in which direction?
Up.
Up. There you go. That's it. Because the other ones are imaginary, we can't plot it. Okay? Let me show you an odd one. Oh, I thought I had an odd one in here. Didn't I have an odd one? You're going to get an odd one up.
Wait. Are we gonna have one?
Yeah.
Of course. We all Come on. If you have an odd function, odd function with 4 terms, more specifically a cubic function. Do you remember the rule for trying to factor that?
No.
When you try to factor something that has an odd value, especially with 4 terms, yeah, exactly. You factor it by grouping. You're going to take GCFs out. So I'm going to factor this by grouping. I'm going to put parentheses around the first 2 terms, plus minus in here. And what's my GCF of x cubed minus 4x squared?
X squared.
X squared. So I take out the x squared. I'm left with x minus 4. What's the GCF of the 25 and 100?
25.
Take out the negative 25, and I get x minus 4. So now I have x squared minus 25, x minus 4, all equaling 0. Can I factor any of that any further?
Yeah.
Which one, Cole?
X squared.
What do you get? X minus 5, x plus 5, and x minus 4. What are your 3 zeros?
5, negative 5.
5, negative 5, and 4.
Why
So you-
isn't it X plus
X squared minus 25 is the difference of squares.
1? Oh.
X minus 5, x plus 5.
Okay.
So this was a 3rd degree polynomial, which means it can have up to 3 possible zeros. And what way are the tails going? Our tails are going like this. It has a 0 at negative 5, has a 0 at 4, and a 0 at 5. So it's got to be increasing through 5. It's got to change direction here and come back up here, doesn't it?
Wait. It's a positive.
It's a positive with an odd exponent.
Not odd X. Okay.
It's a positive with an odd exponent, which means your tails are going up in red.
I see.
Okay. What? Since the drill took away pretty good chunk of time that I wanted to spend on the factory. What I think we're going to wind up doing today is just going to wind up with the stuff on the tails. So let's do this. I've got a little worksheet here that I made up for describing and graphing the polynomial end behaviors. What I want you to do is, for all of these problems, just do the rough sketch of the end behavior, and if it is something like a quadratic that you've been accustomed to factoring, go ahead and try and find your zeros. A couple of these are going to be a little bit trickier than others, but that's why we're just, that 15 minutes kind of wipe this out.
Do you have any more flex passes?
I don't know, probably first hour class took them all.
Because the two that are up there are already signed out. But I really don't understand this.